this one. Now, observational. One of the nicest studies that came from Britain. This guy looked at postmen and postal clerks. And to his surprise, they found the mortality rate among postal clerks were much higher than postmen. Now, what do you think is the reason? Exercise. How do you know? Now, maybe he got cake in each house. You know? Now, the thing is, this is the funny part of observational design. You look at it and then you conclude, oh, that must be the reason. Okay? So, inherent in all observational design is this problem is you make up your mind and say, this must be the cause. Let me design a study for you to start with. I believe that if you apply forceps, the children born will have learning defect. That is my hypothesis. So how will I do the study like that? I am starting the study in 2013. I'll gather a group of children who are all, I'll wait near the labor room, some forceps delivery children, some normal delivery. Now I follow them up. In 2018, they have started going to school. Now I look for learning defect. This is a fairly easy, straightforward cohort design. I have children who are forceps delivery and normal delivery, and I'll measure in both learning defect. Let us say I find more learning defect in this group, forceps delivery. Can I now safely conclude that forceps delivery caused the learning defect? Why not? All right, whole lot of things will happen. But the problem that comes up primarily is, why did the child have a forceps delivery? Was the child compromised in some manner that it required a forceps delivery? Of course, there is learning defect. It would have been more had the child not undergone forceps delivery. Now, this is the bugbear of all observational design. We wish we could do randomized control trials. You know, take 1,000 women, 500 you do forceps, whether they deserve it or not. Forceps, other 500 you force them to a normal delivery, whether they can or not, and then that is not allowed. So we start with a problem in all observational design. One more thing I need to tell you. Supposing I am doing the study very carefully, somebody comes and asks, Dr. JP, what are you doing? And I give this design, and he listens to me very carefully. Wonderful. And you know what the rascal does? He goes and picks up 2008 labor records, finds some children who had forceps delivery, and for some had normal delivery, and quietly comes back. Now they are all 5 years old now, and he finishes studies, and he comes and tells me, I finished your study. Is this design different? What do you think is the difference between this and this? I'm happy you said that. I made you say that. I will never want you to say it ever again, because both these are actually cohort design. Both these start from exposure factor to outcome. In that sense, both are sort of prospective. We call both of them cohort. These are historical cohort. And this is a concurrent cohort. try not use the word retrospective studies. In fact, retrospective study is synonymous with case-controlled design. And in India, somehow, this, at least in medical colleges, the retrospective word has come. Ask the question, what is the researcher doing? What is the sampling frame? Is he selecting people exposed, unexposed, and following them up? Either in real time or in time machine? That's a cohort design. Case control design is different. We choose cases and controls and then look back at exposure. Somebody called it retrospective. I advise you to avoid the word completely, retrospective, because an English word which is used in all kinds of things. So you have historical cohort, concurrent cohort, and case control design. Now I'm going to say something to malign the case control design, only temporarily, okay? Because that's what people do. And then we'll go back and see what a wonderful design this is. Ideally suited for an Indian PG student, because no money, no time, but lots of cases. Case control designs are the ideal one. Now, how do they do case control design? Supposing I'm interested in knowing, does coffee drinking cause pancreatic cancer? This is the way I'll do my case control study in Vellore. I'll contact all the hospitals in Chennai and Bangalore. Hey guys, if you find a case of CA pancreas, please let me have. And I accumulate a few cases quickly. Let's say I get 100 of them of CA pancreas. And then what do? I find out how many drink coffee, how many don't. Let's say 80 drank coffee, 20 did not. And then I choose some controls. I got 100 controls. Who are these controls? For the time being, controls are those without cancer pancreas. Control. And let's say 50 drank coffee, 50 didn't. My study is over. And only thing now I have to do is analyze the data. For analysis, I need 4 letters. A, B, C, D. We use the A, B, C, D so commonly, people think we only know 4 letters, okay? And now I do this little calculation, AD by BC, which is equal to 80 into 50 by 50 into 20. 4. Now, give a bright smile and tell everybody, if you drink coffee, your risk of cancer pancreas is 4 times greater compared to somebody who does not drink coffee. And people give you a suspicious look. Where did that come from? Okay? 4 times. How does that work? Doesn't make sense. And sort of everybody say, case control studies are vague designs. Whole lot of descriptive problem. Now, our task is to make sure at the end of the session, you become believers in case control study. Okay? Let's see if we can do that. To do that, I need to start with a cohort design, which is easy for everybody to understand. I take you to an island. And in this island, I see how many drink coffee, how many don't. So I'm starting with the exposure factor, coffee plus minus. And there were 20,000 people who drink coffee and 10,000 who don't. Now what do? Well, I built a little shack near the beach and start fishing. What else to do? Because cancer pancreas takes years to form. So after gracefully growing older, over a period of time, I get some cases. Here, 16 cases of cancer pancreas. That means 19,984 are normal. Here I get 2 cases of cancer pancreas. That means 9,998 are normal. Now I can't wait any longer. It's been decades. I go for the conference. Now I need to analyze the data. You all know how to do the analysis. Very simple. Incidence of cancer pancreas among coffee drinkers. How much is that? It is 8 per 10,000. How much is that among the non-coffee drinkers? 2 per 10,000. I divide one by the other. And the answer I get is 4. Now when I tell people, if you drink coffee, your risk of cancer pancreas will be 4 times greater as compared to a non-coffee drinker, they are happy. They pat me on the back, they send me to another island to do one more study. But this is very straightforward, very simple. Okay? No ambiguity. Now this is a good starting point. I'm going to take you through certain steps, and I hope you'll hold on, and because at the end of it, you'll suddenly realize it's so neat. Case control designs are. I'm going to label them again A, B, C, D. All right? Now, I'm going to see what I have just done now. I calculated A by A plus B. Do you follow? That is the incidence of disease among coffee drinkers. Then I calculated C by C plus D. Now I divided one by the other and I got relative risk. That's all that I have done. I'm going to make a proposition. Okay, and you should be very suspicious of all people who make proposition. Watch it. I'm going to say A by A plus B is almost equal to A by B, provided A is small as compared to B. Would you agree with that? Almost equal. If A is small in relation to B. Similarly, C by C plus D is almost equal to C by D, provided C is small in relation to D. See, if you have any objection, you should state now. Otherwise, you should keep your mouth shut, okay? And if I divide one by the other, the answer I get is AD by BC, which must be pretty close to relative risk. In fact, if somebody has got a small calculator, you can calculate. This is 4 we are getting. This you'll get 4.002, which is pretty close to 4. All right? Well, I ask the question. We understand what this is. That is incidence of disease among coffee drinkers. What the heck is A by B? A divided by B. What is common about A and B? We are all coffee drinkers. So we have taken the coffee drinkers. What is different between A and B? A have the disease, B don't have the disease. Hey, that is a funny fraction, right? You're dividing the number of people with cancer by the number of people without cancer among the coffee drinkers. It's an odd way of doing it, right? And that's why it's called odds. Odds for what? Odds for cancer pancreas among coffee drinkers. Okay? Now, odds is not a common term we use. When you throw a die, the probability you will get a 6 is 1 by 6. Because there are 6 alternatives, one of them is the one you desire. But when you throw a die, the odds of getting 6 is 1 by 5. One way you get it, 5 ways you don't get it. Odds and probability are 2 ways of measuring chance. They're 2 different ways. Now my statement was, odds will almost be equal to probability if the probability is small. In other words, 16 by 20,000 is almost equal to 16 by 19,984. So this A by B is odds for disease among coffee drinkers. Similarly, C by D is odds for disease among non-coffee drinkers. So when you divide odds for disease with odds for disease, the answer you get is disease odds ratio. Disease odds ratio. And my theme so far has been to tell you that disease odds ratio is almost equal to relative risk if the disease is rare. Remember, we are dealing with cohort design. This is a cohort in Ireland, and so far what I've done is, I told you in a cohort study, you can either calculate a relative risk or an odds ratio, and if the disease is rare, they'll be almost be equal. Any questions so far? Now, in Voxer, Eskimo. Where do Eskimos live? You know Eskimos, where do they live? Igloo. Where is the igloo located? Right. You know, they sit on top of the world. They have a different worldview. They always are sitting there and looking down upon us. This guy comes and says, see, A by B and all I don't like. I like to look from top to bottom. I'm used to doing that. And he puts down A by C. Wretched fellow. Okay, what do you do now? What is common about A and C? They're all cases of, what is the difference? A drink coffee, C don't drink coffee. Hey, we have got a new odds. This is odds for coffee drinking among cancer pancreas. Odds for coffee drinking. Or is odds for exposure among cases. Odds for exposure. Exposure among cases. Eskimo is relentless. He goes and puts B by D. What is common about B and D? They are all non-cases. B drink coffee, D don't. Again, this is odds for exposure among non-cases. Odds for exposure. And he wants us to divide one by the other. Now, when you divide odds for exposure with odds for exposure, you get a brand new odds ratio. It is called exposure odds ratio. Exposure odds ratio. And what do you notice? Both are same. Both are same. And please don't underestimate the discovery. When Bradford Hill first published the paper on smoking and lung cancer, British study, they did not know this. In the whole paper, there is not a word for odds ratio. What is the importance here? Exposure odds ratio is numerically equal to disease odds ratio. So if you calculate one, you have the other. So what's so great about it? That's what I want you to grab today. See, to get incidence of disease among exposed or odds for disease among exposed, you have no shortcuts. You have to wait years for disease to develop. Especially a rare disease, it can be very hard. But what about odds for exposure? It is child's play. You grab some cases and see how many are exposed, how many are not exposed. You follow? And at the end of it, what you calculate is exposure odds ratio. In that sense, it's not very interesting. For example, I do a lung cancer study and I get an exposure odds ratio of 10. What does it really mean? It means odds for smoking among lung cancer patients is 10 times greater as compared to odds for smoking among controls. Who wants to know that? Then you say, hey, wait a minute. Exposure odds ratio is numerically equal to disease odds ratio. So now I can say in the same breath, the odds for cancer among smokers is 10 times greater as compared to odds for cancer among non-smokers. Then you say, hold it. Is lung cancer a rare disease? Of course. That means odds ratio is equal to relative risk. So now I can say the probability that a smoker will develop lung cancer is 10 times greater as compared to a non-smoker. What happened, this case control study is actually short-circuiting a large cohort study. Cohorts are people who have exposed themselves to something. Some have become postmen, some have become postal clerk. Some smoke, some others don't. They are all marching in time. You have a choice. You can assemble them as exposed, unexposed and follow them and grow old with them. Or if you are smarter, what do? You take cases and controls. And you don't need 20,000, 10,000. Find the odds for exposure among cases. Find the odds for exposure among controls. And there you go. You have a measure of relative risk. The brilliant part is this study design is ethically much safer. For example, a friend of mine, she wanted to see if drinking and driving, does it cause road traffic accident? What do you think? Does it? Yes. What is the relative risk? That's what. The relative risk we need. So she was going to do it in California, Los Angeles. So she said, okay, first she thought she'll do a randomized control trial. How do you do that? You take 500 drivers, 250 you give half a bottle of whiskey, other 250 you give lime juice, and send them to the highway. They'll take you and lock you away. You'll never do one more study. So then she said, huh? So she said, okay, I'll do a cohort design. Okay. So how do you do a cohort design? You have lots of investigators, data collectors, send them to different bars, watch that one, 2 pegs of whiskey, that one only Coca-Cola. You keep noting down, gather them, follow them up, see how many have accident. Oh, what a messy design, right? Every night, a bunch of drunk investigators will land up in your house. No way to do a study. Now you look at the ethics part of it, and you watch a guy down 4 drinks, and he's going to get into his car. And then you stand there and watch him. What are you doing? I'm doing observational study. Now, that is not ethically correct, right? But this girl was smart. What she did was, she didn't do all this thing. She waited for a center where all the calls come. This is Los Angeles. For information on accident. Land up there. And the driver is still breathing. You say, excuse me, will you breathe into this? Okay? Then you get exposure for alcohol. How do you get your control? You tarry on for a little while. Wait for the next car to come. Breathe in, boss. Sir, will you be my control, please? There you go. And she did it. Excellent. Ethically, no problem. And valid. So, that is the advantage. That design is much easier to do, less amount of problem, ethical violation problems and things like that. There's another thing you should remember. Many of this study design, a cohort, you need to know what exposure factor are you chasing. Supposing you don't know, what is the exposure factor? Okay, we don't know. For example, irritable bowel syndrome. What are the cause? Nobody knows. So what do? Follow what these fellows did for HIV infection. When AIDS came and hit North America and people started losing immunity, what did they do? They decided to do case control design. Now, what is the advantage of case control design? Remember, in my study in first, I showed coffee as one factor. I could have chosen tea, Ovaltine, Horlicks, any number. Each one will provide a 2 by 2 table. That's what they did. They thought of a whole lot of variables and measured in immune deficient patients and controls. Okay, to see where is the association. This is called a fishing expedition. Everything is allowed because you don't know what's causing it. So go for a fishing expedition. And they got the culprit. You know what it was? Amyl nitrite. Have you heard of amyl nitrite? It's something you pop. You go high on amyl nitrite. They say sex after amyl nitrite is great. Anyway, they thought the first article came, amyl nitrite causing immunosuppression. They had an article nicely written. They put biological plausibility. Maybe amyl nitrite went through the nose, into the lung, and tickled up your T4 cells. Whole lot of story they wrote. Suddenly they realized it's not the amyl nitrite. It's what they did after the amyl nitrite that is causing AIDS. Okay? So you may not get it in the first pass, but you will. In other words, as an investigative epidemiologist looking for something unknown, this is an excellent area of research. Methodology. So, have I convinced you it's a good design? Any questions?
Confounding factors.
I've said the good things, the bad things are coming. All right? But one question you should ask, but then this can only be done in a rare disease, right? I told you this works only for a rare disease. And now, can you tell me a common disease? What are the incidents? I tell you one thing. I told you rare, common, and all things. I never gave you a time frame. Diarrhea is a common disease. Okay. But if you ask the question, how many people are sitting in the various toilets in Mumbai now? Now then that is a rare disease. So in other words, you can design case control study. We capture cases and controls in time, just like we did in accident. At the time the cases and controls are selected, these slices in time. It doesn't matter much. Okay? That is a problem. Now, so basically I would like you to remember that it works out in most instances. I'll give you a mathematical reason to say that. Look at this. Most diseases, incidence of sputum positive pulmonary tuberculosis is one of the common conditions we face here, is 1 per 1,000. So if you write it in a calculator and put 1 divided by 1,000, is it up? Time up? No. You get 0.001. If you convert it to odds, you write it 1 by 999, which is equal to 0.001001. Both are equal. So if a thing as common as sputum positive pulmonary tuberculosis, the incidence of 1 per 1,000, odds ratio should be equal to relative risk. Make it something more common. 1 out of 100. What is that 1 out of 100? Let's say incidence of what? Oh, not a 100, 1%. Incidence much higher. Somebody else with the same key, okay? It's 0.01. But if you write 1 by 99, it works out to 0.0101. Something as common as 1% incident still be all right. Take something very, very, very strong, much more common. 10%. Acute brain damage after listening to epidemiology lecture. Now, if you write that 1 by 9, ha, ha, now you get different. In other words, in most diseases, this works perfectly well. Okay? And there are three basic problems with any observational studies. This is not peculiar to case control studies. It is for same cohort. Number one is selection bias. Number two, information bias. Number three, confounding. I have just enough time to squeeze those three notions in your mind. I mentioned about irritable bowel syndrome. And below they want to do a study. And what they did was, they get enough cases. For some strange reason, many of our patients come from Northeast, from Meghalaya. And if somebody develops irritable, do you also get from that area? No. They somehow take a Guwahati-Trivandrum Express and land up in Katpadi, that's below. So they have enough. So they thought it is some sort of problem with personality type. Is there a psychiatrist here? Personality type. There are psychiatrists classify people into type A, type B, Bush, and all things, that kind of people. Anyway, finally what happened, when they got this, they wanted controls. Cases are mainly from Meghalaya. How do you take controls? Can you take from Tamil Nadu? Didn't look reasonable. So we suggested you go to Meghalaya and take a control. Now that is traveling too far, right? Then they had a brilliant idea. They said, we'll take the attendant who comes along. Now wait a minute, we have a problem. We're talking about personality type. Here is an attendant who's a relative or friend who, when he hears the friend has got irritable bowel syndrome, decides to take leave, pack his bag, gets into the train, Guwahati-Trivandrum Express, and travels all the way. Now mind you, it's not easy to travel with a guy who has got irritable bowel syndrome. Okay. Now that fellow is a guy, of a different caliber. Now you can't use him as a control. They look very different. So in control selection, you need a bit of an art. And selection bias is a very, very important problem. And but I just wanted to mention this to say, I said nice things about case control design, but you need an expertise to do it also. Remember, violin is a glorious instrument in the hands of an expert. But the same instrument you give it to a novice, he'll chase you out of the room. Okay? Same thing with case control design. It's an excellent design. So when you're doing something, you need help in terms of control selection. The second I said is information bias. Now that is quite common. First of all, we have a problem with investigator bias. This fellow has got cancer, that fellow's control doesn't have. So you go and ask the fellow, have you smoked? No. Are you sure? No. Not ever, not even one. In college once, smoker. Go to the control fellow. Control fellow. You don't smoke. Not really. Okay, non-smoke. So, that bias is strong, especially from the investigator point of view. But even otherwise, just think of doing a study. Let's say congenital malformation. A newborn baby has a malformation. Is it something that you aid during pregnancy, radiation, you want to do? You ask the mother of the child who is deformed. Now, delivering a baby which is deformed is the most shattering experience a woman can have. And what does she do? She goes through the entire pregnancy again and again, thinking, God, what did I do wrong? What did I do wrong? So when you give her later on and meet her and say, did you take any medicine during pregnancy? 13. Correctly she'll tell, because she remembers every day of her pregnancy. What about the control? Control is the mother who's produced a healthy baby. She has forgotten she has ever been pregnant. Okay? So any question you ask, no, you can't compare. So the recall bias among the reporters are also a big source of anxiety. Now, I said this not to say discourage you. We take into consideration these in designing the study to overcome these problems. And finally, the last bit. This is that I'm going to give you an example of a randomized controlled trial, and look at these numbers. We have got drug and placebo, cured, not cured. These are information on males, and this is for females. Drug, placebo, cured, not cured. Now look at the data. Look at the cure rate among drug here, among males. What is the cure rate? 60%. What is the cure rate for placebo? Again, 60%. Okay? Now look at the women. So the drug obviously doesn't work for men because both for drug and placebo is same. Look at this side. Drug cure rate is 30%. Placebo also 30%. The drug is no good for women either. Now I want you to help me put these two tables into one composite table. I hope you can see at the back. Drug, placebo, cured, not cured. 120, 30, 150, 150, 300. Here it is 120, 180, 300. Can you see that? So the cure rate here is 50%, drug, and placebo is 40%. 40%. So here is a drug which is not good for men, not good for women, but good for people. How come? Most of these questions, if you do answer correctly, you get a medium-sized chocolate. Any thoughts? I know for you it's too far away. Forgive me. This is not case and count. They are drug and placebo. There are 300 who got the drug, 300 who got the placebo. See, 300, 300. Give it another try. More men got the drug, more women got the placebo. So what? So what? Why not? You should tell me why not.
The disease does worse in women.
Huh?
The disease does worse in women. No, it does, which is why you can't compare.
Huh?
It should be equal among both the genders, the drug and placebo.
According to Indian Penal Code.
But because the disease does worse in women, it should be equal. You have to stratify for sex.
Hmm? Hmm? Pardon?
Something minus here plus doctor minus.
That's it. What you do is, I'm going to draw a triangle. I want to draw it in your mind. You should always remember. When you're trying to study the effect of a drug on cure, or it could be exposure on an outcome, doesn't matter. There's always a possibility there will be something else standing and confusing you, and we call it a confounder. I'm trying to explain the concept of confounding using these two tables. Now, look at this. You all diagnose one part of the problem smartly. There were more men who got the drug, more women got placebo. If you're a man, you're more likely to be in the drug group. And if you're a woman, you're more likely to be in the placebo group. Now look at this. Placebo men. What is the cure rate? Placebo men. 60%. Look at placebo women. What is the cure rate? 30%. men enjoy a higher cure rate by virtue of the fact they are male. Okay, men have a higher cure rate. Now come back to this. Is the confounder here is gender? Is sex related to cure? Yes. Men have a higher cure rate than women. So that part of the triangle is complete. Second part, is sex associated with a higher risk of being given the drug? Yes. We have completed the triangle of confounding. In other words, this what you see, a better cure rate among men, is reflected, and you make a mistake of saying drug cures. Drug doesn't cure. It's the gender that cures. Okay? So that is a problem for all study designs based on observational design, and we need to learn how to overcome it. I'm not stating these problems exist without saying it can't be solved. All of them can be solved. Even a confounders that we have, we can solve it through proper analysis. Thank you very much.
Thank you. Thank you, Dr. JP. Anybody wants to ask something? Yeah? You want to ask something? Okay. Microphone. She wants to ask you something.
Sure. So this is the whirlpool of confounder factor. What are the ways to get out of it, just in brief? What do we need to
There are
look
two
at?
methods in case control designs. One is called matching. Match. Now, Rajul, you said yesterday matching, but in general, in modern time, we hesitate to match. Okay? Matching means generally gender, maybe age, because the other remedy for confounding is to adjust. I'm sorry, I'm saying the word adjust. In India, when you say we can do adjustment, oh yeah, adjustment. Now, it's not political adjustment. I'm talking about proper statistical analysis. So that's excellent way of controlling. So you don't have to worry about all you have to do is document suspected confounders.